Hey folks, today we're going to talk about SVD, which is nothing but singular value decomposition. This is in continuation to the previous two videos. We spoke about the spectral theorem and then EVD, eigenvalue decomposition, and now we talk about SVD, right? So before we talk in detail about SVD, I'm going to just set the context. We will also talk about the differences between spectral theorem, EVD, and SVD. SVD is nothing but yet another matrix decomposition or a matrix factorization technique. Again, widely used in data science projects and machine learning. The objective is again to transmit in bits and pieces, dimensional reduction, feature extraction, and data compression. You kind of decompose a matrix into smaller chunks and you can transmit it basically to reduce the cost and reduce the complexity while retaining the essential information. Just remember the two examples we spoke about, the image processing and the facial recognition in spectral theorem and EVD, right? So remember spectral theorem we spoke about, it handles symmetric matrices, diagonalize it, and basically in an orthogonal matrix format for transmission, right? The decomposition form there was a matrix A is nothing but you do a diagonalization of an orthogonal matrix, which is Q D Q transpose, right? Or in a video we spoke in terms of PDP transpose. Similarly, eigenvalue decomposition is again for a square matrix, basically not essentially just for symmetric matrices, unlike spectral theorem. And here the decomposition format of A matrix will be in the form of PDP inverse, right? And we spoke about Y inverse in the previous video. Now coming to SVD, what SVD does is this is basically for a rectangular matrix, right? Basically it's not just for square matrix, but it's also for a rectangular matrix. So instead of a square matrix like an n cross n, you can over here decompose a m cross n matrix, right? That's what the objective of SVD is. So basically what SVD does is it breaks down the matrix into three components, and the three components here are U, V, and sigma. And it transmits each of them separately or in whatever fashion we require, and then you can use it for retransmission. So that's what decomposition means here for SVD, right? So now let's look at a quick representation of it in a mathematical term, right? The matrix A is nothing but it's the product of U, sigma, and V transpose. That's the representation. Now what is U? It is nothing but it's one of the orthogonal matrix, which is the left singular vector. We'll talk more in detail. Sigma is the diagonal matrix, and the V transpose is the right singular vector orthogonal matrix, right? We'll talk in terms of a Python code as well as the steps to compute SVD. Again, this is very simple, just three steps. One is compute the value of V, compute the value of U, and then compute the value of sigma, and then multiply all of it, and you will get the same matrix A. That's why A is nothing but the multiplication of U, V, and sigma, right? From a Python code perspective, it's pretty straightforward. You just need to import NumPy as a library, define the matrix. The matrix over here that I'm using is 101 minus 2 1 0, and then you just use this line to perform SVD, which is nothing but np dot linear algebra dot SVD, and using the matrix A, and then you print the results of U, sigma, and V transpose, you get the result, right? And if you want to prove this is working, just do the multiplication of the three and you will get nothing but A, which is 101 minus 2 1 0. That's how you prove it, right? Now this is pretty much straightforward when it comes to Python. Now let's talk about it when it comes to numerically solving it. So again, there are a lot of calculation in terms of eigenvalues and eigenvectors. I won't go into it because that's already covered in the previous video. So basically the steps here are, you have the matrix 101 minus 2 1 0. The first step is you compute A transpose A, and also you compute AA transpose, and you can do that using a Casio FX991 CW calculator. It's pretty straightforward. Once you do that, you also need to do the eigenvalues for A transpose A as well as for AA transpose, right? So the eigenvalues for A transpose A here will be lambda 1 is 6, lambda 2 is 1, and lambda 3 is 0. The summation, the sigma is nothing but you just take roots of lambda 1 and lambda 2 and lambda 3, you get that value. and that you substitute in sigma in a diagonal format, right? So 2.4495, which is lambda 1, and then the lambda 2 is 1, and the rest of all is all 0. And then you form the eigenvectors of A transpose A, we have seen in the previous video. And after that, you kind of do the U part, which is AA transpose. So we did A transpose A, and then you do the same methodology for AA transpose. You get lambda 1, lambda 2, substitute that, and then once you're done with it, you can verify the reconstruction by multiplying UE and U sigma and V transpose, and you'll get the same value of A, as you could see, right? So the bottom line here is you get the values of U, V, and U sigma and V transpose. The objective here is, if you want to transmit anything, you do it one matrix at a time, right? And you can kind of re-get it on the other side of it. That's the objective of using this. Any questions, put in the comments, and more than happy to answer anything that you may have. Thank you.